Okay, let's get right into it. Something just happened in space that's making us rethink everything we thought we knew about satellite internet. We're talking about a tiny laser, a truly mind-boggling distance, and a result that, honestly, almost sounds like science fiction. First, let's just try to wrap our heads around the distance here. The signal in this test came from a satellite in geostationary orbit. That's a staggering 36,000 kilometers away from Earth. To put that in perspective, that's nearly a tenth of the way to the moon, and it's way, way higher than the low Earth orbit where services like Starlink zip around. Now for the power source. The laser that beamed this signal across that enormous void, it was only 2 watts. I mean, think about that. That's actually weaker than the little light bulb inside your refrigerator. A tiny little pinprick of light sent across a vast expanse of space. So this is the real head-scratcher, right? How on earth can a laser that weak, from that far away, deliver speeds that reportedly just blow the competition out of the water? Well, that's the puzzle we're going to piece together today. To really get what makes this so revolutionary, we first need to understand that there are 2 totally different ways to build a satellite internet network. I kind of like to think of it as the swarm approach versus the sniper approach. So on one side, you've got the low Earth orbit, or LEO model. This is Starlink's playbook. It's the swarm. You have thousands of satellites flying pretty close to Earth, only about 550 kilometers up, basically blanketing the entire globe. On the other side, you have this new test from geostationary orbit, or GEO. This is the sniper, a single satellite parked way, way up there, aiming a super precise beam at a specific target. You don't need as many satellites, but man, that is a much, much harder shot to make. And here are the results of that sniper shot. While Starlink's medium download speed is a very respectable 67 megabits per second, this single laser test clocked in at 1 gigabit per second. That's 1,000 megabits per second. We're talking roughly 5 times faster. The performance leap is just undeniable. But how in the world did they pull it off? And that brings us to the secret sauce. The technology that can take a blurry, distorted signal from space and somehow make it perfectly clear. This breakthrough comes from a team of researchers at Peking University and the Chinese Academy of Sciences. They've developed this dual system called AO-MDR synergy. You can think of it like a 1-2 punch. First, you've got adaptive optics, or AO, which is actively fixing the garbled signal in real time. Then, mode diversity reception, or MDR, swoops in and cleverly recovers any bits of light that got scattered on the journey down. So why do you even need all this fancy tech? Well, sending a laser through 36,000 kilometers of empty space, that's the easy part. The really hard part is that last little stretch through our own atmosphere. All the turbulence and moisture and dust. It basically acts like a wobbly, unpredictable lens. You know when you look through the shimmering heat haze rising from a hot road and everything gets all distorted and blurry? It's exactly like that, but for a data signal. So here's how the system at the Lijiang Observatory cracks that problem. The laser beam comes down from the satellite and gets all scrambled by the atmosphere. But on the ground, an array of 357 tiny, super-fast mirrors starts moving, physically reshaping the laser's wavefront to cancel out every bit of that distortion. At the same time, the system recovers the scattered light and folds it back into the main signal. And boom, what you get is a clean, stable, and incredibly fast connection. And the data proves just how well this works. Before they flipped the switch on this correction system, only about 72% of the signal was stable enough to actually use. But with the AO-MDR system running, that number jumped to over 91%. That is a massive improvement in reliability, which, as you know, is absolutely crucial for any kind of high-speed data transfer. Now, a technology this powerful isn't just about streaming movies faster. No, this has some really profound strategic implications. For starters, the incredibly narrow, focused beam of a laser is much, much harder to intercept or jam than a wide radio broadcast. That makes it perfect for secure military communications. It's also a game changer for deep space missions, giving us the ability to control probes on the Moon or Mars with much greater precision. And finally, it helps us sidestep the growing traffic jam in the radio frequency spectrum that pretty much all of our current wireless tech depends on. The bottom line is, we're kind of hitting the limits of what radio waves can do. That spectrum is getting incredibly crowded and it's heavily regulated. Lasers, or what they call optical communication, basically open up a whole new frontier with way more bandwidth and almost no interference. This could be a fundamental shift in how we move data around the planet and beyond. So, all of this naturally raises a huge question about the future of global communications, and of course, the race to control it. But, and this is a big but, there's a world of difference between one successful experiment and a fully functioning global network. The next massive hurdle for China is figuring out how to scale this up, deploying more of these incredibly advanced satellites, and building a whole network of these sophisticated ground stations to catch the signals. That is not a small task, believe me. And that leaves us with this final, really provocative thought. We're essentially watching two completely different philosophies for space-based internet play out in real time, the swarm versus the sniper. So is the future going to be delivered by thousands of satellites all working together in a massive swarm? Or could just a handful of incredibly powerful, precise lasers from high orbit completely change the game? That's a question worth thinking about.